Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to give more examples related to explaining whether the function given is continuous or not. And in this specific example, it is asking you to define the intervals such that each function here is continuous. Okay, so for question A here, you can see that the function given is a polynomial function, and we know that based on what you have seen before, when you have a polynomial function, this function is going to be continuous at every number in their domains. So for the first question here, what you need to do is you need to start off by thinking about the domain of this function. Okay, so what is the domain of a function? Again, when you talk about the domain, you are interested to find what are the values of x such that when you substitute the values into the function, then there will be no sort of problem whatsoever. So when you substitute the values into the function, there is no issue with the calculation. Okay, there is no issue with the computation or with the calculation. All right, so we need to think about all those values. So for question A here, since this is a polynomial function, we know that if you substitute the values between negative infinity to infinity, there will be no issue with this function. So therefore, the domain of this function is going to be the value of x, where x is going to be all real numbers. So real numbers consist of any value from negative infinity to infinity. Now the question is asking a specific interval such that the function here is continuous. Well, therefore, the interval such that this function here is continuous, the interval such that this function is continuous is going to be equal to, since this is a real number, the interval is going to be from negative infinity, doesn't include negative infinity. So notice here that we are using the round bracket to infinity. Okay, so this is the interval such that the function here is continuous. Okay, now let's move on to question B. So this is a function, this is a rational function. We have numerator and denominator, and usually when you have a rational function, you need to pay a close attention to the denominator, and you have to ensure that the denominator is not going to be 0, because if it is 0, then you will have a computational problem. So in this case, what we can see is we want to make sure that x squared minus 1 cannot be equal to 0. Okay, it's not equal to 0. X squared is not equal to 1. So x cannot be equal to plus minus square root of 1. So therefore, x cannot be equal to plus minus 1. So there are two values here that x cannot take, which is 1 and negative 1. If you substitute 1 or negative 1 into this function, the denominator is going to be 0, and you will have issue with the computation. So therefore, the domain of this function is going to be the values of x, and okay, hold on, let me just explain this part here. So if you look at this numerator part, there is no issue. This is just a polynomial function, and basically any value of x is okay. Okay, so any values of x is okay. So x can be real numbers. Therefore, for gx here, the domain is going to be x, where x is going to be all real numbers except x equals to plus minus 1. So x can take any value from negative 1 to positive, x can take any value from negative infinity to infinity, except it cannot take value 1 and negative 1. And again, we have to answer the question here, which is, it is asking you to define the interval where the function is going to be continuous. So therefore, the interval such that the function is continuous is going to be from negative infinity to negative 1. It doesn't include negative 1. And it will be union with negative 1 and 1. And it will be union with 1 and infinity. So these are the intervals. So these are the intervals where the function given here will be continuous. Okay, next we're going to look at question C, and I'm going to erase the ink on this slide. Okay, so for question C, we have quite a number of functions brought up together. So we can think of this function as function f(x). This could be a different function, which is gx maybe, and this could be another function, which is kx. And we have seen that from here, we know that if you have a combination of functions, so we have a function that can be from the combination of simple function, and therefore if we know where the functions are continuous at, therefore the combination of that simple function will also be continuous at that specific point. Yeah, so if we go back to this example here, now I'm going to consider these functions separately and determine the domains for each of them, and based on that we can think about the intervals such that function hx here is continuous. Okay, so for fx is equal to square root of x, and usually for this function here we don't have issue in the computation, because as long as the value of x here is greater than or equal to 0. Notice that if x is negative, you cannot compute the square root of a negative value. So in this case, the domain for fx is going to be x, where x is greater than or equal to 0. So that's the domain for fx. Next, let's consider the domain for gx. So gx is x plus 1 and x minus 1, and again we have a rational function over here, and what you need to pay attention is at the denominator part, where you have to ensure that this is not going to be 0. So x minus 1 cannot be equal to 0, and x is not equal to 1. So if you plug in the value of 1 into this, you will have a computational issue for gx. And therefore, the domain for gx is going to be x of real numbers. We're going to have the values of x where x are all real numbers. X are real numbers. That means x can take values from negative infinity to infinity, but except x equals to 1. So except x equals to 1, the rest of the values are okay for function gx. Okay, next is let's look at function kx. So kx is x plus 1 and x squared plus 1. And again, when you have a rational function, you need to pay attention to the denominator part. And because we have x squared plus 1, we will have no issue with computation because there is no way for this value to become 0. The value here is always going to be a positive value, regardless of whatever value of x is considered here. So in this case, the domain for kx is going to be all values of x such that x is any real number. So x are all real numbers. It can be any values from negative infinity to infinity. Now, based on these three functions given here, we need to come up with the domain for hx. Okay, and so the domain for hx, we have to consider the requirement that is tighter. Okay, because we need to make sure that the values of x that we choose here fit the whole the three of the functions given here. And because of that, the domain for hx is going to be all values of x. So based on these three answers given here, we can see that this is tighter. X greater than or equal to 0 is tighter than x real numbers. Okay, we have to make sure that this is considered as the answer, because if you consider x is a real number, then if you plug in the negative value inside here, then this function cannot be computed at all. So that will affect function hx. Okay, therefore the domain for hx is going to be this one, x is greater than or equal to 0. And this also needs to be considered because this is also a tighter restriction that you need to consider. Well, except x equals to 1. Okay, so this is the domain for hx, and therefore the interval such that hx is continuous is going to be, so notice that this is x greater than or equal to 0, so we will be using a square bracket to denote that 0 is included. It's going to be from 0 to 1 except x equals to 1. So x equals to 1 is not included, so we're going to use the round bracket, and this will be union with 1. Greater than or equal to 0 means it can go on forever until positive infinity. So it's going to be from 1 to infinity. So it doesn't include infinity, it doesn't include 1 here. So that's the interval such that hx is continuous. Okay, I think that's all for now. Thank you very much for watching.